we are being asked to compute the moment about point O. So let's go ahead and draw our system. We're going to have this kind of cantilever type system here. Here's point O. And this member is at an angle here with a vertical of 60 degrees. And we have an applied force acting right here of 3 kips. And this applied force is at an angle of 50 degrees from the vertical, okay? So, and then, I need another dimension line for you. This diagonal length is 5 feet. All right, so again, we're being asked to compute the moment about point O. Now, how is this problem different than what we've seen before? Well, not only is the force at an angle, but the member itself is at a different angle. So notice the member itself is at its own angle of 60 degrees from a vertical axis, and the applied force is at its own different angle of 50 degrees from a vertical axis. So how do we tackle this? Well, there are a couple different ways we can actually solve this. So here's the first way I'm going to do it. I'm going to call this solution 1, okay? And what I'm going to do is I'm going to investigate perpendicular distances between the force components and point O. All right, so here's how we're gonna do this. We're gonna I'm gonna redraw the system. That's an ugly line, isn't it? That's a little better. And here is that 60-degree angle. Let's put little 2 tick marks there. And our 3 kips is going to be resolved into a vertical component and a horizontal component. All right, so how about we call this a little f sub y, a little f sub x. All right, and of course, you know, this makes up the 3 kips here. There's the 50 degrees. All right, now go ahead and put the 5 feet in there too. Now, the next thing we need to look at are the perpendicular distances from each of these force components to point O over here. So if we're looking at the perpendicular distance between Fy and point O, we're going to have this horizontal distance. What about the perpendicular distance between Fx and point O? Well, we're going to have this perpendicular distance, right? This vertical perpendicular distance is the distance between Fx and point O, all right? So the next question is, how do we obtain the perpendicular distances properly? So we're going to have to resolve this distance into a vertical and horizontal component, all right? So I'm going to call this horizontal distance d sub x. I'm going to call this vertical distance d sub y. So putting it all together, we can say that the moment about point O, taking counterclockwise as positive, is going to be f sub y, right? F sub y times its perpendicular distance, dx. All right, and that's causing a counterclockwise tendency of rotation, so that'll be a positive value. And then we're going to have plus f sub x times d sub y. How do I know that? Well, again, here is my line of action of f sub x, and here is dy, its perpendicular distance. All right, and then f sub x is also causing a counterclockwise tendency of rotation about point O, thus giving it a positive value right here. All right. So the question is, how do we piece all these together? Well, let's do it just one at a time. We can get all four of these pieces, no problem. We have enough information here, right? So let's get the forces first. Let's get F sub y. F sub y right here is going to be equal to 3 kips times the cosine of 50 degrees. And let's see what that comes out to be. 3 times cosine 50. I get 1.93 kips. And then F sub x is 3 kips times the sine 50 degrees. 3 times sine 50. I get 2.30 kips. Alrighty. And then what about dx and dy? So let's go ahead and get the dx component first. We're looking right here. How are we going to get that? Well, that's just going to be equal to 5 feet times the sine of 60 degrees, right? And when we punch that through, we get 4.33 feet. And then dy is going to be 5 feet times the cosine of 60 degrees. And that should just be 2.5 feet. All right. Now what we can do is piece all of this together into our moment equation and compute that moment about 0.0. So when we put all this together, we have 1.93 kips times 4.33 feet plus 2.30 kips times 2.5 feet. And putting all that together, what do we get? I get 14.1 kip feet. All right. And that's a net positive. So it is causing a counterclockwise tendency of rotation. So that is the answer. Now, I want to tackle this from a different perspective as well. So down here, I'm going to call this solution 2. Now, under solution 2, I personally believe solution 2 is more computationally efficient than solution 1. It's gonna we can put this together much more efficiently and quicker with solution 2. However, it is a little tougher to look at. So you have to kind of have an eye for geometry to be able to put solution 2 together adequately. So let's practice that though. The only way to get good at it and develop that eye is if you practice. So here's our member. Here's our 3 kips for sure. And let's go ahead and put these angles in here. There's 60 degrees. Here's the 50-degree angle, all right? And then the diagonal length is 5 feet. All right, so here's how we can piece some things together. First, I'm going to go ahead and project this dashed reference line down. I'm going to put like a little makeshift set of axes right here at the end of this member, all right? And then what I'm going to do is I'm going to project my 3 kip force, this line of action of the force, down here. Now, I'm not changing its angle of orientation. I'm not changing the 50 degrees. I'm just kind of stretching that vector out and elongating its tail. And then I'm going to put in a little perpendicular line right here, okay? So what I've formed here is this right triangle, okay? I've formed this right triangle right here. Now, in the right triangle, the hypotenuse is the 5 feet. In fact, let me go ahead and move that 5 feet maybe on the outside of it so it's a little more clear, all right? Now, since I've projected the tail of this vector back here to a point where it's perpendicular to my point of interest, guess what? That has enabled me to form this as my perpendicular distance. So I'm going to go ahead and label that as such. I'm going to call this right here my perpendicular distance d. So now what I can do is I can say 3 kips times that times d, and that's it. That's my moment about point O. Now the question is, oh, low battery, look at that. The question is, how do you get this perpendicular distance d right here? How do you figure that out? Well, the way we do it is by looking at this right triangle right here, okay? So I know this is a right triangle, but what about these other angles? Do I know anything about this interior angle right here? Well, sure I do. So here's what we need to think about. We're gonna say that this angle right here is 60 degrees. Can we say that? Absolutely. Check it out. We have 2 parallel lines here cut by a transversal, right? That's the member itself. So it's creating alternate interior angles which are congruent, and these are both 60 degrees. So this 60 degrees comes from the fact that this is also 60 degrees over here. Now, what can I then deduce about this angle right here? Well, notice that this is what's called a vertical angle. That's 180 degrees. So that interior angle of the triangle right here is going to be equal to 180 minus 60 minus 50, okay? So I'll make a note of that. I'm going to say this angle right here is 180 degrees minus 60 degrees minus 50 degrees, which gives me a 70 degree angle. Okay, that's 70 degrees inside of that. So now I know that this right triangle has an interior angle of 70 degrees right here. And because I know that, I can now say the moment about here's point O, the moment about point O, counterclockwise positive, is equal to 3 kips times 5 feet times the sine of 70 degrees, right? Because again, if this is 70 degrees and I need this distance right here, d, right? Then I say hypotenuse times the sine of this 70 degree angle gets me this component d right here. So this right here is d. All right. One more time. How about I peel this triangle out for us so we can get a better look at it. This is d right here. This is 70 degrees. This is 5 feet. So again, I could say sine 70 degrees equals d over 5 feet. And then, of course, d equals 5 feet sine 70 degrees. That's just doing some trigonometry off to the side. So I punch this through, and let's see what we get. We get 3 times 5 times sine of 70. Sure enough, we get 14.1 kip feet, which matches our answer from our earlier solution.